Hello, this is Ben Budenstein, and this is Lab 2, Lines of Charge. So introduction. So the goals of this lab are to prepare two pieces of charged clear tape to determine the interaction between charged tape and other charged objects, calculate the amount of excess charge on one piece of charged tape, and we're going to treat the charge of a single piece of tape as being uniformly distributed along its length. And in the end, we're going to show simulations with the computational model. So the preliminary findings are that the charged clear tape had a net positive charge. The charge on the tape was 2.39 times 10 to the negative 8th coulombs, and the tape is deficient of 8.34 times 10 to the 10th electrons. So some concepts we use for Newton's second law, which is the force of an object equals the change in momentum over time, or the change in time, and the gravitational force, where m is the mass of the object, and g is the acceleration due to gravity, and it always points in the negative y direction. We also use the electric field for a rod with uniformly distributed charge, which is the equation shown below. Since the tape is no longer treated as a point charge, the charge is now assumed to be evenly distributed along its length. It's treated as a uniformly distributed charge, and the E field considers separation distance between the tape and the observation point, as well as the length of the tape. So we also use Coulomb's law, which is equal to the product between the Coulomb constant K, which is shown below, and the quotient between the two charges and the square of the distance between the charges, multiplied by the vector r hat. Is also equal to the product of the charge at the observation point and the net external electric field. And then K equals 1 over 4 pi sigma naught. So the assumptions are the charge was evenly distributed along the tape, and we ignore air resistance, and both tapes have the same amount of charge. Lab 1 recap. The interaction between the two U-tapes they repelled each other. Interaction between the U-tape and the pen was an attraction. And there was also an attraction between the U-tape and the hand. So we knew that the pen was negatively charged, therefore the tape must be positively charged. The separation distance was 0.025 meters. So these are the free body diagrams. The system is the same as it was last time, suspended by U-tape. The suspended U-tape, the surroundings were the held U-tape. Force 1 on the suspended U-tape was the electric force from the held U-tape on the suspended U-tape. Force 2 was the force of gravity. On the held U-tape, force 3, which points up, is the holding force, and force 4, which points down, is the electric force from suspended U-tape on the held U-tape. The lab, this is also from lab 1. Tape length was 0.18 meters, tape width was 0.19 meters, surface area was 0.03342 meters squared, and the vertical separation distance of the two tapes was 0.025 meters, which is also our mag. Calculations. So use the equation for electric fields of a uniformly charged rod to estimate the charge of the tapes. You set the magnitude of the force of the electric force equation to the magnitude of the gravitational force on the tape. The electric force equals the product of the charge of the external field, electric field, and we treated the top tape as the observation point and the bottom tape as the charged rod, and those are your equations next to it. So in this computational model, you can see that we have the constants identified, the mass of the tape, the net charge, as well as the distance apart. And then we calculated the E field, which is based on the equations previously shown. And then we calculated E force. And then for the loop, it showed the iteration of the code going through the different pieces of the tape because they all had the same charge because it was uniformly distributed along the length. And then you can see we calculated our force vectors, and then it gave us this diagram, and you can see that the E field points away from the charged tape, and they're all the same magnitude because they all have the same charge at each piece. So in the discussion, the charge of the tapes Q equaled 2.39 times 10 to the negative 8th coulombs. Based on the estimation charge and using a quick guess and check method to find the value of the charge that gives an electric force that's equal to the force due to gravity. It was 8.34 times 10 to the 10th electrons deficient. The charge on the tapes are positive based on observations. For the U-tapes to float, the net force must be 0. This leads to the force due to gravity being equal to the magnitude due to the electric force from the held U-tape on the suspended U-tape. Possible sources of error: inaccurate measurement of the length and width, inaccurate measurements of the separation distance, which could have been due to the U-tapes not being held parallel, and rounding errors as well. What if you had modeled each of your tapes as a single point charge, like in the previous lab, compare estimated values? So the point charge in lab 1 was 1.35 times 10 to the negative 8th coulombs, and the line charge model in lab 2 was 2.39 times 10 to the negative 8th coulombs. The line charge has a much greater charge than the point charge model, a factor of 1.7. Why do these estimates differ? What is closer to the real value? The difference is due to us considering charge being uniformly distributed along the rod-like structure instead of just a point charge, and a line charge is valued to the real value. Is closer to the real value. Thank you very much.